Hi all, good day. I am Johnny Carlos Salavaria. Welcome to Operating Systems class. And today we're going to be discussing about Chapter 6, the CPU scheduling. Scheduling deals with how we are going to run processes. So our aim or objective would be the following. We would like to introduce the concept of CPU scheduling, which is the basis for multi-program operating systems. We would like to describe different CPU scheduling algorithms, also to discuss the evaluation criteria for choosing a CPU scheduling algorithm for a specific system. And last is to examine the scheduling algorithms of some operating system. So in conjunction with our objectives, the content of our discussion would be dealing with the basic concepts of CPU scheduling, the scheduling criteria, which will be the premise for our comparison of the different scheduling algorithms. And we have thread scheduling, multi-processor scheduling, then we have real-time CPU scheduling, and then some operating system examples, and last would be the evaluation of the algorithms. So once we say we are to schedule our CPU, what we are trying to do is we would like to maximize our CPU utilization, the number of programs and processes we take and execute within a unit of time, so that should be maximized. And we say it is with respect with multi-programming. So almost all processes alternate between two situations in a continuing cycle called the CPU I/O burst cycle. So CPU burst and then followed by an I/O burst, and then it loops. So our main concern would be the CPU burst distribution to maximize the use of our CPU. So in the figure is an example of a CPU I/O burst cycle. So in a simple system running on a single processor, the time spent waiting for an I/O is wasted, and those CPU are lost forever because the CPU then just sits idle at that time while waiting for the I/O. So a scheduling system allows one process to use the CPU while another is waiting for I/O, thereby making full use of their otherwise lost CPU cycles. So CPU bursts vary from process to process and from program to program, but an extensive study shows frequency patterns similar to that shown of figure. So it shows that the short CPU bursts occurs more often compared to longer CPU bursts, or the short CPU bursts have higher frequency than those with longer CPU bursts. So, so next is CPU scheduler. The CPU scheduler, also known as short-term scheduler, selects from among the processes in the ready queue and then allocates the CPU to one of them. So the queue may be ordered in various ways. The storage structure for the ready queue and the algorithm used to select the next process are not necessarily first in, first out. There are several alternatives to choose from, as well as numerous adjustable parameters for each algorithms. So the CPU scheduling decisions may take place when a process switches from running to waiting state, such as in an event of an I/O request, when a process switches from running to ready state, for example in response to an interrupt, it switches from waiting to ready state, such as at completion of an I/O, and then when the process terminates. So if the scheduling takes place only under conditions 1 and 4, the system is said to be non-preemptive or cooperative. So it is said to be non-preemptive because under these conditions, Once a process starts running, it keeps running until it either voluntarily blocks or until it finishes. So let's investigate the conditions. So for case 1 and 4, there is no choice but to select a new process. So when it is blocked or it is terminated. So this the process is put into waiting state or the process is terminated or when it's done, finished. So for case 2 and 3, the scheduler either continues running the current process or selects a different one. So we say that all other scheduling is preemptive. So when we are dealing with a preemptive scheduling, we should consider some conditions. So we should consider access to shared data. So preemptive scheduling can cause problems when two processes shares data because one process may get interrupted in the middle of updating shared data structures. So race conditions discussed in chapter 5 covers the better of it. Then consider preemption while in kernel mode. So preemption can also be a problem if the kernel is busy implementing a system call when the preemption occurs. Then we should consider interrupts occurring during crucial OS activities. So next we have the dispatcher. So dispatcher module gives control of the CPU to the processes selected by short-term scheduler or the CPU scheduler, which involves switching context switching. So one job which is already in the CPU has been taken out, and then a new process is loaded. So switching to user mode, and then jumping to proper location, the user program that restarts the program. So in the case where there is context switch, it needs to execute from the step where it was left. So the dispatcher needs to be as fast as possible as it runs on every context switch. So the time consumed by the dispatcher to stop one process and start another is known as the dispatch latency. So there are several different criteria to consider when trying to select a scheduling algorithm for a particular situation environment. So we really cannot say one scheduling algorithm is better than the other because there will always be trade-offs. So one algorithm is better than the other on a case-to-case basis, depending on particular situations and environment. So this includes CPU utilization. So we want to keep the CPU as busy as possible. So ideally, the CPU would be busy 100% of the time. So as to say, it is working optimal. So when on a real system, CPUs should range from 40%, which is for light loaded, and then to 90% for heavy loaded system. Next criteria would be the throughput, where the system should be able to completely execute as many processes as it can per unit of time. So the total amount of work done in a unit of time. And then we have the turnaround time. So this is the amount of time to execute a particular process. Turnaround time doesn't necessarily mean execution time of a program. So it may entail additional time from context switching or dispatcher latency and the waiting time. Next, we have the waiting time, the amount of time a process has been waiting in the ready queue. So the waiting time is like time spent stuck in traffic. Then we have the response time, the amount of time it takes from when a request was submitted until the first response is produced. It doesn't necessarily mean the output or time sharing environment. So in general, we want to optimize the average value of a criteria. For example, dispute utilization, throughput, minimize all others. So ideally, we want the CPU scheduling algorithm that optimizes all criteria simultaneously. But this is not generally possible. So instead, we choose an algorithm based on its ability to satisfy a policy. So we proceed with the scheduling algorithm optimization criteria. So mostly we want to maximize CPU utilization, maximize throughput, minimize turnaround time, minimize waiting time, and then minimize response time. So now that we have discussed the optimization criteria, next we discuss the different scheduling algorithms. So note that the following sections will explain several common scheduling strategies looking at only a single CPU burst each for a small process number of processes. So first come first serve scheduling. This is the first scheduling algorithm. Uh, this is by far the simplest scheduling algorithm. So it is implemented in first in first out queue, like customers falling in line at the bank. So let's have an example. Given process P1, P2, and P3, given that they have burst times of 24, 3, and 3 respectively. So suppose that the processes arrived in the order of P1, P2, and P3. So we can chart, as we can see in the figure, P1 with 24, P2 with 3, and P3 with 3 burst times, CPU burst times. So um, computing for the waiting time, the waiting time for P0 would be 0 since uh, it does not wait for any other processes to complete. Then the P2, it waits for P1 to complete, therefore it waits for 24 burst time. And then P3 would wait for P1 and P2 to complete, so having 27 burst times. So therefore the average waiting time would be 17. Okay, suppose we have another example. Suppose that the process arrived in the order of P2, P3, and then P1. So we have uh, P2 having a waiting time of 0, P3 we having a waiting time of 3, and then P1 a waiting time of 6. So with this, we have an average waiting time of 3. So we have a better uh, better waiting time results than the previous example. So it matters on the order the process arrived. So to note, the total runtime for the three process is the same despite the order, but the second example had better case or have better average waiting time. So thus, this result to having a much better than the previous case. So we have convoy effect. And the short process are behind longer processes. So consider one CPU bound and many other I/O bound processes. This produces the convoy effect. Like the previous case, when P1 is on top of first rather in order than P2 and P3, so it hogs the CPU, and then later. So let's proceed. Shortest job first scheduling. So the shortest job first scheduling associates with each process the length of its next CPU burst. So it uses the length to schedule the process with the shortest time. The idea behind this shortest job first is to pick the quickest, fastest little job that needs to be done. Get it out of the way first, and then pick the next smallest, fastest job to do next. So technically, it picks the process based on the next shortest CPU burst, not the overall process time. So let's look at this example. So given the processes P1, P2, P3, and P4 with burst times 6, 8, 7, and 3 respectively. So we have the shortest job first scheduling chart with given this. So the shortest burst time would be 3 for P4, so meaning this would be the first, and then next would be the P1 with 6, and then next would be P3 with 7, and last would be P2. So given this, the average wait time is 3 for P1, 16 for P2, and then 9 for P3, and 0 for P4. So the average waiting time would be 7. So basically, we just order the process with respect to its burst times. So the lower the burst time, the higher its priority in the ordering. Okay, so the shortest job first can be proven to be the fastest scheduling algorithm, meaning it is optimal. It gives minimum average waiting time for a given set of processes, but it suffers from one important problem. How do you know how long the next CPU burst is going to be? So, difficulty of knowing the length of the next CPU requests. One could ask the user, but this is for long-term batch jobs. In short-term CPU scheduling, it does not work. Next, another option would be to statistically measure the runtime characteristics of job, particularly if the same tasks are run repeatedly and predictably. But once again, that really isn't a viable option for short-term scheduling in the real world. So a more practical approach is to predict the length of next CPU burst based on some historical measurement of recent burst time for this process. So one simple and fastest relative accurate method is to be using the exponential average. So given with this formula, where T of n is the actual length of the nth CPU burst, then the tau n plus 1 is the predicted value for the next CPU burst, and then we have an alpha where alpha is between 0 to 1. So the formula is the predicted value for the next CPU burst is equal to the alpha times the actual length of the nth CPU burst plus 1 minus alpha times the length, the previous uh, predicted value. So in this scheme, the previous estimate contains the history of all previous times, and alpha serves as weighing factor for the relative importance of recent data versus past history. So uh, most commonly, alpha is set to 1/2. So the shortest job first can either be preemptive or non-preemptive. Preemption occurs when a new process arrives in the ready queue that has a predicted burst time shorter than the time remaining in the process whose burst is currently on the CPU. So, preemptive version of the shortest job first is the shortest remaining time first. So we have the prediction of length of the next CPU burst, so given by that formula. So given with this formula here, so and then given having alpha with set to 0.5 or half, 1/2. So we have these a alpha tn plus 1 minus alpha of the previous. So we get these formula here. So given this data, we can have the next guess, which is 8. So half of 10 is 5, and half of 6 is 3. So 5 plus 3 would yield 8. Then the next would be half of 8 plus half of 6, no 4, I mean, would yield half of 8 would be 4, half of 4 would be 2, so if 4 plus 2 would yield 6, so on and so forth. It would yield a guess. That's how to yield the what you call this, guess. So um, given this, the examples of exponential averaging. So if alpha is set to 0, then by this formula, if alpha is 0, we can see that the measured burst times are ignored, right? So when alpha is 0, t of n is 0, and then we just assume a constant burst time. So the recent history does not count when alpha is 0. So t, the previous would just be equal to the current, or the next prediction would be just equal to the previous prediction. So when alpha is set to 1, the prediction would be equal to alpha of t of n. So meaning the past history of predictions will be ignored and assumes that the next burst will be the same length as the last burst. So only the actual last bursts count. So if we expand the formula, we get uh, the prediction tn plus 1 to be these values. So a tn plus a minus 1 minus a times a tn minus 1, because we substituted tn with tn minus 1 and then so on and so forth. So since both alpha and 1 minus alpha are less than or equal to 1, then each successive term has less weight than its predecessor. So now we go to the example of the shortest job first preemptive version, which is the shortest remaining time first. Now we add the concept of varying arrival time and preemption to the analysis. So process P1 to P4 with burst times 8, 4, 9, and 5 respectively, with arrival of 0, 1, 2, 3 respectively. So the resulting preemptive SJF Gantt chart would be as follows. So let's investigate. P1 starts at 0 since it is the only process in the queue, and then after time 1, P2 arrives. So when we evaluate for the remaining time for process P1, we get 7 milliseconds. And then P2 with 4. So therefore, P1 is preempt and process P2 is scheduled. So at time 2, P3 arrives. So at this point, we have P1 with 7 milliseconds, P2 with 3 milliseconds remaining, and then we have P3 with 9 milliseconds. So the shortest job is the P2. So it still continues the process. So then after time 3, P4 arrives. So now at this point we have P1 with 7 milliseconds, then P2 with 2 milliseconds left, and then P3 with 9, and then P4 with 5. Thus still the P2 will have the shortest remaining time, so it still continues. And then at time 5, process P2 completes, and then we evaluate another process with the shortest time, so which we have a P4. So P4 with a 5 milliseconds, and then after completion we evaluate again, get the order P1, because P1 has 7 milliseconds left, and then followed by P3 with 9 milliseconds. So calculating for the average waiting time, we have for P1 10 milliseconds minus 1, because it is started here at 0, so minus 1, plus P2 started at 1, but since it arrived at 1, minus 1, so plus P3 with waiting time of 17 minus the arrival time of 2 milliseconds, plus a P4 with waiting time of 5 milliseconds minus arrival time of 3, with the average of 6.5 milliseconds. So this case, for the preemptive version, we have better results compared to the shortest job first non-preemptive version, which have average waiting time of about 7 milliseconds. So next we have priority scheduling. So in this scheme, a priority number, mostly implemented using integers, is associated with each process. So the CPU is allocated to the process with the highest priority. So the smallest integer would be the highest priority. So it can either be preemptive or non-preemptive. So the shortest job first is a priority scheduling. The previous scheduling algorithm, where priority is the inverse of predicted next CPU burst. In short, the smaller the expected burst, the higher the priority. So with this scheduling algorithm, this scheduling can suffer from a major problem known as indefinite blocking, or so-called as starvation, in which the low priority tasks can wait for very long period of time, or maybe forever, indefinite, because there are always some other jobs around that have higher priorities. So one common solution to this problem is aging. So aging, in which priorities of job increases the longer they wait. So under this scheme, a low priority job will eventually get its priority raised high enough that it gets run. So let's have an example. So given the process P1 to P5, excuse me, priorities with 3, 1, 4, 5, and 2 respectively, with burst times 10, 1, 2, 1, and 5 respectively. So the priority scheduling Gantt chart would be uh, in just in order with its priority. So with P2 with priority 1, so it goes first with burst time of 1, and then going with the second priority P5 with burst time of 5, so it gets 6, done at 6. And then next would be the third priority, which is P1 with burst time of 10, so 6 plus 10, 16. So at 16, at time 16, P3. The next priority after 3 is 4, so P3 with burst time of 2, 18, and then P4, which is the last priority with a burst time of 1, total of 19 milliseconds. So computing for the average waiting time, we have 8.2 milliseconds. So we have 1 plus 6 plus 16 plus 18 plus 0 because P2 have 0 waiting time. So we have the average waiting time of 8.2 milliseconds. Next we have the round-robin scheduling algorithm. So this scheduling algorithm uses preemptive policy. So the round-robin scheduling algorithm is designed especially for time-sharing systems. It is similar to the first-come, first-served scheduling, but preemption is added to enable the system to switch between processes. So each process gets a small unit of CPU time called the time quantum. So usually it is 10 to 100 milliseconds. So after this time is lapsed, the process is preempted and added to the end of the ready queue. So if there are n processes in the ready queue and the time quantum is q, then each process gets 1 over n of the CPU time in chunks of at most q time units at once. So no process waits more than n minus 1 q times units. And so the timer interrupts every quantum to schedule the next process. And thus, the round-robin scheduling can give the effect of all process sharing the CPU equally, although the average waiting time can be longer than with other scheduling algorithms. So next we go to an example to have it. So given a time quantum of 4, we have here. So with the process P1 with burst time 24, P2 with burst time 3, P3 with burst time 3. The Gantt chart would be this as follow. So we start with P1. So P1 has 24 burst time. So given with this, it does not complete at after 4 milliseconds. It is then preempt and then proceed to P2 with burst time of 3 seconds. So after 7 milliseconds, P2 completes and then proceed to P3. P3 with burst time of 3 milliseconds less than the time quantum. So P3 completes at 10 milliseconds. So then afterwards it goes to P1 with 24 no wait 20 burst time remain. 24 starting with 24 milliseconds, it has a remaining of 20 milliseconds. So it executes the P1. So after 14 milliseconds, so still with time quantum of 4, it stops. It preempts P1 and then evaluates again. But since there is nothing left in the queue, we have P1 again run for another 4 milliseconds and then again for another 4 milliseconds until it finish up to 30 milliseconds. So typically the round robin have higher average turnaround than the previous, the shortest job first, but has better response time. So the performance of the round robin algorithm is sensitive to the time quantum selected. So the time quantum should be large compared to the context switching time. So time quantum usually is 10 milliseconds to 100 milliseconds. Context switch less than 10 microseconds. So if the quantum value is large enough, then the round robin is reduced to the first come first serve algorithm. So it's similar to first in first out. So if the time quantum is very small, then each process gets 1 over nth of the processor time and shares the CPU equally. But a real system invokes overhead for every context switch, and then the smaller the time quantum, the more context switch there are. So as we can see in the figure below, having a time quantum of 12, we have no context switches. For having a process with burst time of 10, so if we have quantum time of 6, then we have 1 context switch, and if we have a quantum of 1, we have 9 context switches. So as I said earlier, the performance of the round robin scheduling algorithm is sensitive to the time quantum selected. So also, the turnaround time also varies with quantum time in a non-apparent manner. So consider, for example, the process shown in the figure. So these with processes P1 to P4 with the burst times of 6, 3, 1, and 7 respectively. When the time quantum is 1, we get the average turnaround time of 11, and time quantum is 2, we have 11.5, and 3, somewhere 10.8, I guess, and then 4, we have 11.5, so in 5 is 12.3, and then when the time quantum is 6 and 7, it sticks to 10.5. So in general, Turnaround time is minimized if most processes finishes their next CPU burst with one time quantum. And so a rule of thumb is that 80% of CPU bursts should be smaller than the time quantum. So, multi-level queue. So another class of scheduling algorithm has been created for situations in which processes are easily classified into different groups. So ready queue is partitioned into separate queues. For example, the common division is made between foreground processes or interactive processes and the background batch processes. So these two types of processes have different response time requirements and so may have different scheduling needs. So under this algorithm, jobs cannot switch from one queue to another. So once they are assigned a queue, that is their queue until they're finished. So each queue has its own algorithm. Mostly foreground processes uses the round robin algorithm, and then the background process runs in batches. So first come first serve is the best algorithm to use since the order doesn't matter much and it has the least context switching. It runs pretty fast and better use of CPU utilization. So in addition, there must be scheduling amongst the queues. The scheduling must be done between the queues. Most modern operating systems uses the fixed priority scheduling, where it serves all from foreground and then from background, but there would be possibility of starvation. So another possibility is to time slice among the queues. Here, uh, each queues get a certain portion of the CPU time, which it can be then scheduled among its various processes. For instance, in the foreground background queue example, the foreground queues can be given 80% of the CPU time for round-robin scheduling amongst its processes, while the background queues receives 20% of the CPU time to give to its process on first come first serve basis. So here we are looking at an example of a multi-level queue scheduling algorithm with 5 queues listed below in order of priority. So we have the system processes, the interactive processes, the interactive editing process, the batch process, and then the lowest priority is the student processes. So each queue has absolute priority over lower priority queues. So here, no process in the batch queue, for example, could run unless the queues for system process, the interactive process, and the interactive editing process were all empty. And so, for example, an interactive editing process entered the ready queue while the batch process was running, then the batch process would be preempt. Next, we have multi-level feedback queues. Multi-level feedback queue scheduling is similar to the ordinary multi-level queue scheduling described previously, except that jobs may be moved from one queue to another for a variety of reasons. So aging can also be incorporated so that job that has waited for a long time can get bumped up into a higher priority queue for a while. So multi-level feedback queues is most flexible because it can be tuned for any situation. But it is also the most complex to implement because of all the adjustable parameters. So the multi-level feedback queue scheduler is defined by the following parameters: the number of queues, the scheduling algorithm for each queue, the method used to determine when to upgrade a process, the method used to determine when to demote a process, and the method used to determine which queue a process will enter when that process needs service. And so next we move to an example for multi-level feedback queues. So given this figure here, we have three queues. Q0, which has round robin scheduling with a time quantum of 8 milliseconds, and then the Q1 with round robin time quantum 16 milliseconds, and then Q2 with first come first serve scheduling algorithm. So the scheduling, a new job enters Q0, which is served in a round robin. So it gains the CPU. The job receives 8 milliseconds. And then if the process does not finish within 8 milliseconds, the job is moved to Q1. Then at Q1, if the job is again served round robin, receiving a 16 additional milliseconds. So after executing and still it does not complete, it is preempt and then it's moved to Q2, which is implemented in first come first serve. So that is for a single process. So that's how the process moves from one queue to another. So if it does not complete, it moves down to the other queue and then still same to the other. But the implementation for scheduling is that only when Q0 is empty will it execute processes in the next queue, Q1. Similarly, the process in Q2 will be executed only if Q0 and Q1 are empty. And so, if a process that arrives for Q1 will preempt a process in Q2. So in similar manner, a process in Q1 will be preempted by a process arriving at Q0. Next, we have the thread scheduling. So in the previous chapters, we were introduced to the thread process model, distinguishing between user level and the kernel level threads. So on operating systems that support them, it is the kernel level threads and not the processes that are being scheduled by the operating system. And so, on systems implementing many-to-one and many-to-many threads, thread library schedules user-level threads to run on lightweight process known as process contention scope, since scheduling competition is within the process, where this is typically done via priority set by programmer. And so to decide which kernel level threads to schedule into the CPU, the kernel uses system contention scope. So the competition for the CPU with the system contention scope scheduling takes place among all threads in the system. Next, we go to pthread scheduling. The pthread library provides for specifying scope contention. So we have pthread scope process, which schedules threads using PCS by scheduling user threads onto available lightweight processes using the many-to-many model. And then we have the pthread scope system schedules thread using the SCS by binding user threads to particular lightweight process, effectively implementing a one-to-one model. Note that on some systems, only certain contention scope values are allowed. For example, Linux and Mac OS X system allows only the pthread scope system. So next we have here an illustration of a pthread scheduling API. So the program first determines the existing contention scope and then set it to the pthread scope system. So this part here um, determines the existing contention scope, this if else, and then here it sets it to the pthread scope system. So, so from here it then creates 5 separate threads that will run using the SES scheduling policy. So the num thread, which is 5, so it creates 5 separate threads. So our discussion so far has focused on the problems of scheduling the CPU in a system with a single processor. So now we will deal with multiple processor scheduling. CPU scheduling problems become more complicated when there are multiple CPUs available, because now there is more than one CPU which must be kept busy and in effective use at all times. Multiple processor systems may be heterogeneous, which means we have different kinds of CPU, or homogeneous, which means all the same kind of CPU. But in this section, we concentrate on systems in which the processors are identical, or called homogeneous, in terms of their functionality. And so there are two approaches to multiprocessor scheduling. So the first approach uses asymmetric multiprocessing, uh, where only one processor accesses the system data structure, alleviating the need for data sharing. So here, one processor is the master server, who handles all server scheduling decisions, I/O processing, and other system activities. And the rest of the processors only execute the user code. Now the second approach uses symmetric multiprocessing, SMP, where in each processor is self-scheduling all processes in common ready queue, or each has its own private queue of ready process. So in here, we must ensure that two separate processors do not choose to schedule the same process and that the processes are not lost from the queue. So virtually all modern operating systems supports SMP, including Windows, Linux, and Mac OS. So currently it is the most common. Processors contain cache memories, which speed up repeated accesses to the same memory location. So if a process were to switch from one processor to another each time it got a time slice, the data in the cache for that process would have to be invalidated and reloaded from the main memory, thereby obviating the benefit of the cache. So because of the high cost of invalidating and repopulating cache, most SMP systems try to avoid migrating from processor to processor of the processes. Instead, it attempts to keep a process running on the same processor. So this is known as the processor affinity. So a process affinity takes several forms. It can be soft affinity. So when an operating system has a policy of attempting to keep a process running on the same processor, but does not guarantee that it will do so. It is called the soft affinity. When it is allowing a process to specify a subset of a processor in which it may run, then it would be a hard affinity. Many systems provide both soft and hard affinities. For example, Linux implements soft affinity but also provides the scheduled uh, sched set affinity system call, which supports hard affinity. So the main memory architecture of a system can affect processor affinity issues. So the figure illustrates an architecture featuring non-uniform memory access, or NUMA, in which a CPU has faster access to some parts of main memory than other parts. So typically this occurs in a system containing combined CPU and memory board. The CPU on a board can access the memory on the board faster than they can access memory on the other board of the system. So here in the figure, the CPU, given the same board, it has a faster access than it can access on the other board. So if the operating system's CPU scheduler and memory placement algorithm work together, then a process that is assigned affinity to a particular CPU can be allocated memory on the board where that CPU resides, so to get a faster access. So on SMP systems, it is important to keep the workload balanced among all processors to fully utilize the benefit of having more than one processor. So load balancing attempts to keep workload evenly distributed across all processors in an SMP system. So there are two general approaches to load balancing. First would be the push migration, which periodic task checks load on each processor and if found pushes task from overloaded CPU to the other CPUs. So the other approach is the pull migration. The pull migration occurs when an idle processor pulls a waiting task from a busy processor. So push and pull migration need not to be mutually exclusive and are in fact often implemented in parallel on load balancing systems. So interestingly, load balancing often counteracts the benefit of the processor affinity, which is discussed in the previous section. That is, the benefit of keeping a processor running on the same processor. The, the benefit of keeping a process running on the same processor, rather, is that the process can take advantage of its data from being in the processor's cache memory. So either pulling or pushing a process from one processor to another removes this benefit. Traditionally, SMP systems have allowed several threads to run concurrently by providing multiple physical processors. However, a recent practice in computer hardware has been to place multiple processor cores on the same physical chip, resulting in multi-core processors. So in here, each core maintains its architectural state and thus appears to the operating system to be separate physical processors. So the SMP systems that uses multi-core processors are faster and consumes less power than the systems in which each processor has its own physical chip. You know, researchers have discovered that when a processor accesses a memory, it spends a significant amount of time waiting for the data to become available, which is known as the memory stall, which may occur for various reasons such as cache miss, accessing the data that are not in the cache memory. So to remedy this situation, many recent hardware designs have implemented multi-threaded processor cores, in which two or more hardware threads are assigned to each core. This takes advantage of the memory stall to make progress on another thread while memory retrieve happens on another thread. Here we have an example, this figure above, example of a single-threaded processor core where memory stalls and compute cycle um, alternates. So in this scenario, the processor can spend up to 50% of its time waiting for the data to become available from the memory. So as we can see, the thread computes, and then memory stall happens, then computes, then another memory stall, so on and so forth. So this figure below illustrates the dual-threaded processor core on which the execution of thread 0 and the execution of thread 1 are interleaved. So if the first thread is stalled while waiting for the memory, the other thread is switched. And so by assigning multiple kernel threads to a single processor, memory stalls can be avoided or reduced by running one thread on a processor while the other thread waits for memory. Next, we have real-time CPU scheduling. The CPU scheduling for real-time operating systems can present obvious challenges. In general, we can distinguish between soft real-time system and hard real-time system. So, soft real-time systems has no guarantee as to when critical real-time process will be scheduled. They guarantee only the process will be given preferences over non-critical processes. And so when this happens, they have degraded performance if their timing needs cannot be met. So example of this would be streaming video. Now, hard real-time systems task must be serviced by its deadline. So service after the deadline has expired is the same as no service at all. So these are systems that they have total failure if their timing needs cannot be met. So example of this would be the assembly line robotics, automobile airbag deployment, and so on and so forth. So now we consider the event-driven nature of a real-time system. So when an event occurs, the system must respond to and service it as quickly as possible. So we refer to event latency as the amount of time that elapses from when an event occurs and to when it is serviced. So usually different events have different latency requirements. So here we have the type of latency that affect the performance. The interrupt latency refers to the period of time from the arrival of an interrupt at the CPU to the start of the routine that services the interrupt. So that would be the interrupt latency. Now the amount of time required for the scheduling dispatcher to stop one process and start another is known as the dispatch latency, which is covered previously. So providing real-time tasks with immediate access to the CPU mandates that real-time operating system minimizes this latency as well. The most effective technique for keeping dispatch latency low is to provide preemptive kernels. So as we can see in the figure at the right, we have the uh, interrupt latency, the illustration of the interrupt latency. So first, it determines the interrupt type, and then context switching, and then the ISR. So from this point up to the ISR is the interrupt latency. So now in um, the figure, we diagram the makeup of dispatch latency. So the conflict phase of dispatch latency has two components. So first is the preemption of any process running in kernel mode. So here, so we have here, and then the release by low process of resource needed by high priority processes to dispatch. So overall, this is the event latency. So here we have the overall is the event latency. Here we have the interrupt latency, and then here we have the dispatch latency. So that's that. So now we proceed to priority-based scheduling. So the most important feature of a real-time operating system is to respond immediately to a real-time process as soon as the process requires the CPU. So for a real-time scheduling, scheduler must support preemptive priority-based scheduling. Note that providing a preemptive priority-based scheduler only guarantees a soft real-time functionality. So for hard real-time system, it must further guarantee that real-time tasks will be serviced in accord with the deadline requirements. And making such guarantees requires additional scheduling features. Before we proceed with the details of the individual schedulers, however, we must define certain characteristics of the processes that are to be scheduled. So first, the processes are considered periodic here. So that is, they require the CPU at constant intervals. So once a periodic process has acquired the CPU, so it has a fixed processing time, and then it has a deadline D by which it must be serviced by the CPU, and a period P. And so the relation of the processing time, the deadline, and the period can be expressed as this formula here. So P is greater than or equal to D greater than or equal to T greater than or equal to 0. Then the rate of periodic task is 1 over P. And so schedulers can take advantage of these characteristics and assign priorities according to a processor's deadline or rate requirements. So here we see the figure. You can see that the P must always be greater than the D, which is greater than the T period for each period. So next we proceed to the rate monotonic scheduling. So the rate monotonic scheduling algorithm schedules periodic tasks using a static priority policy with preemption. So priority is assigned based on the inverse of its period. Shorter period, higher priority. Longer period equals lower priority. So the rationale behind this policy is to assign a higher priority to tasks that requires the CPU more often. Furthermore, Rate monotonic scheduling assumes that the processing time of a periodic process is the same for each CPU burst. That is, every time a process acquires the CPU, the duration of its CPU burst is the same. Now let's consider an example. We have two processes P1 and P2. So now we must first ask ourselves whether it is possible to schedule these tasks so that each meets deadline. So if we measure the CPU utilization of a process as a ratio of its burst to its period, the CPU utilization of this would be Ti over Pi, so uh, the processing time for P1 20 over the period 50 plus the processing time of P2, which is 35 over the period, which is 100. So 20 over 50 would result into zero point 0.4, and 35 over 100 would result into 0.35, which is a total of 0.75 or 75%. Therefore, it seems we can schedule this task in such a way that both meet their deadlines and still leave the CPU with available cycles. So now suppose we assign P2 a higher priority than P1, so in which uh, P2 starts execution first and completes at 35. At this point, P1 starts. It completes its CPU burst at time 55. However, the first deadline for P1 was time 50, so the scheduler has caused P1 to miss its deadline. Now suppose we use rate monotonic scheduling, in which we assign P1 a higher priority than P2, because the period of P1 is shorter than the P2. So the execution of these processes in this situation is shown in this figure. So P1 starts first and completes its CPU burst at time 20, thereby making its first deadline. So P2 starts running at this point and runs until 50. It runs until time 50. So at this time, it is preempted by P1, although it still has 5 milliseconds remaining to its process CPU burst. So P1 completes its CPU burst at time 70, at which point the scheduler resumes with P2. So P2 completes its CPU burst at 75, also meeting its first deadline. Then the system is idle until time 100, when P1 is scheduled again, so the next period report. So overall, both processes complete at time 75, and the CPU is then idle for 25 time unit before the process repeats. So rate monotonic scheduling is considered optimal amongst algorithms that uses static priority, because any set of processes that cannot be scheduled with this algorithm cannot be scheduled with any other static priority scheduling algorithm either. There are, however, some sets of processes that cannot be scheduled with static priorities. For example, this. Suppose we have two processes P1 and P2 having a period of 50 and 80 respectively, and then having a processing time of 25 and 35 respectively, and the deadlines matches the period. So we compute for the overall CPU usage. So we have 25 over 50 for P1 and then 35 over 80 for P2. So we have zero point 0.5 for P1 and 0.44 for P2, total of 94% CPU utilization. So this indicates that it would be possible to schedule the processes. So with the rate monotonic scheduling, P1 goes first because it has um, shorter period. So again, P1 goes first and completes its first burst at time 25. Then P2 goes next and completes at 25 out of 30, out of its 35 times unit before it gets preempted again by P1 at time 50. So P1 completes its second burst at 75, and then P2 completes its last 10 times unit at time 85, missing its deadline of 80 by 5 times unit. So despite being optimal, the rate monotonic scheduling has a limitation. CPU utilization is bounded, and it's not always possible to fully maximize CPU resources. So the worst case CPU utilization for scheduling n process is n times 2 to the power 1 over n minus 1, which is 100% for a single process, but drops to 75% for two processes and to 69% as n approaches infinity. Note that in our last example, 94% is higher than 75%. So since the combined CPU utilization is approximately 94%, above the 75% of for two processes, therefore the rate monotonic scheduling cannot guarantee that they can be scheduled so that they meet their deadlines. So next would be the earliest deadline first scheduling, or the EDF scheduling, which dynamically assigns priorities according to deadline. So the earlier the deadline, the higher the priority. So the later the deadline, the lower the priority. Now to illustrate EDF scheduling, we again schedule the process before P1 and P2 with the period having 50 for P1 and then 80 for P2. And then the process time would be 25 for P1, 35 for P2. And then the deadline would be the same as with the period here, as shown in this table. So the EDF scheduling is shown, illustrated by this figure below. So since process P1 has an earlier deadline, so it is initially have higher priority than that of process P2, right? So process P2 begins running at the end of CPU burst for P1. However, whereas rate monotonic scheduling allows P1 to preempt P2 at the beginning of its next period at time 50, the EDF scheduling allows process P2 to continue running. So P2 now has higher priority than P1 because its next deadline is at time 80. So is earlier than P1 at time 100. So thus both P1 and P2 meets their first deadline. So process P1 again begins running at time 60 and completes its second CPU burst at time 85, so also meeting its second deadline at time 100 here. So P2 is then preempt because P1 has an earlier deadline at time 150 here. So then P2, which is at time 160. So at time 125, P1 completes its CPU burst, and then P2 resumes its execution, finishing at time 145, and thus meeting its deadline as well. So the system is idle until time 150, and P1 is scheduled to run once again. So unlike the rate monotonic algorithm, EDF scheduling does not require the process be periodic, nor must a process require a constant amount of CPU time per burst, I mean. The only requirement is that a process announces its deadline to the scheduler when it becomes runnable. Next, we go to proportional share scheduling. So proportional share schedulers operates by allocating T shares among all processes in the system. So an application receives N shares where N is less than T. So this ensures that each application will receive N over T of the total processor time. So for example, assume that we have a total of 100 shares and it is to be divided among three processes A, B, and C. So we have the A assigned with 50 shares, the B assigned with 15 shares, and C assigned with 20 shares. So this scheme ensures that A will have 50% of the total processor time, and then B will have 15%, and C will have 20%. And so proportional share scheduling works with an admission control policy. So not starting any task if it cannot guarantee the share that the task that it needs. So given in our example, if a new process D requested 30 shares, the admission control would deny D entry into the system. And so next we have the POSIX real-time scheduling. So the POSIX standard also provides extension for real-time computing, the POSIX 1B standard. So here we cover some of the POSIX API related to scheduling real-time threads. So POSIX defines two scheduling classes for real-time threads, the sched FIFO and the sched RR. So the sched FIFO schedules tasks in a first-in, first-out order with no time slicing among the threads of equal priority. On the other hand, sched RR uses a round-robin policy. So it is similar to the sched FIFO except that it provides time slicing among threads of equal priority. So the POSIX API specifies the following two functions for setting the scheduling policies. So this here, the pthread after attr underscore get sched policy, and the pthread attr attribute set sched policy. So it's the setter and the getter. And so the first parameter to both functions is a pointer to the set of attributes for the thread. And then the second parameter is either a pointer to an integer that is set to the current scheduling policy, that is for the getter, or an integer value, sched FIFO, sched RR, or sched others, for the set function. So both functions return non-zero values in an if an error occurs. So here we illustrate a POSIX pthread program using this API. So this program first determines the current scheduling policy, and that here we use the getter so to determine the current scheduling policy, and then sets the scheduling algorithm to sched FIFO. So we turn next to the description of the scheduling policies of Linux, Windows, and Solaris operating systems. It is important to note that we use the term process scheduling in general sense here. So in fact, we are describing the scheduling of kernel threads with Solaris and Windows system, and of tasks with Linux scheduling. So process scheduling in Linux has had an interesting history. So prior to kernel version 2.5, the Linux kernel ran a variation of traditional Unix scheduling algorithm. So from version 2.5, moved to a constant order of uh, 01 scheduling time at versions 2.6 that ran a constant time regardless of the number of tasks, and provides better support for SMP systems. However, it yields poor interactive performance. So the Linux scheduler is a preemptive priority-based algorithm with two priority range, time sharing and real time. So real time from 0 to 99, and the nice range from 100 to 140. So unlike Solaris or XP, Linux assigns longer time quantums to higher priority tasks. And so a runnable task is considered eligible for execution as long as it does not consume all the time available in its time slice. So those tasks are stored in the active array, so indexed according to priority. So when a process consumes its time slice, it is then moved to an expired array. So the task priority may be reassigned as part of the transferal. So when the active array becomes empty, the two arrays are swapped. These are stored in run queue structures, so on multiple processor machines. Each processor has its own scheduler with its own run queue. So this version worked well on SMP systems, but has poor response time for interactive processes. So during development of the 2.6 kernel, the scheduler was again revised and is released 2.6.3 of the kernel, which is called the Complete Fair Scheduler, which became the default Linux scheduling algorithm. And so scheduling in Linux systems is based on scheduling classes. So each class is assigned a specific priority. By using different scheduling classes, the kernel can accommodate different scheduling algorithms based on the needs of the system and its processes. The scheduling criteria for a Linux server, for example, may be different from those for a mobile device running Linux. So to decide which task to run next, The scheduler selects the highest priority task belonging to the highest priority scheduling class. The standard Linux implements two scheduling classes. One is the default scheduling classes using the CFS scheduling algorithm and a real-time scheduling class. So rather than using strict rules that associate a relative priority values with the length of the time quantum, the CFS scheduler assigns a proportion of CPU processing time to each task. This proportion is calculated based on the nice value assigned to each task. The nice value range from -20 to +19, where numerically lower nice values indicate a higher relative priority. Tasks with lower nice values receive a higher proportion of CPU processing time than tasks with higher nice value. So the default nice value is 0. By the way, the term nice comes from the idea that if a task increases its nice value from say 0 to +10, therefore it is being nice to other tasks in the system by lowering its relative priority. And so CFS doesn't use discrete values of time slice and instead identifies a targeted latency, which is an interval of time during which every runnable task should run at least once. So target latency can increase if the number of active tasks in the system grows beyond a certain threshold. So the CFS scheduler doesn't directly assign priorities. Rather, it records how long each task has run by maintaining the virtual runtime of each task using the per task value v runtime. So this is associated with a decay factor based on the priority of tasks. So lower priority tasks have higher rates of decay than higher priority tasks. And so for tasks at normal priority, which is have a nice value of 0, so virtual runtime is identical to actual physical runtime. And so to decide which task to run next, the scheduler simply selects the task that has smallest v runtime value. So in addition, a higher priority task that becomes available to run can preempt a lower priority task. And so here we have the CFS performance. Here the Linux CFS scheduler provides an efficient algorithm for selecting which task to run next. So basically each task is placed in a red-black tree, which is a balanced binary search tree whose key is based on the value of the v runtime. So given the tree below, it's this figure. So when a task becomes runnable, it is added to the tree, and if the task is not runnable, then it is removed. So tasks that have been given less processing time or having smaller values of v runtime are towards the left side of the tree, and so the inverse would be at the right side, so the tasks that have been given more processing time. So because the red-black tree is balanced, navigating to discover the leftmost node will require the O of log of n operations, where n is the number of nodes of the tree. However, for efficiency reasons, the Linux scheduler caches this value in the variable rb leftmost, and thus determining which task to run next requires only retrieving the cache value. So continuing, real-time scheduling according to 206-1B. So real-time tasks have static priorities. So the figure below maps the real-time plus the normal map into global priority scheme, where normal tasks are assigned a priority based on their nice values, where a value of -20 maps to priority 100, and then a nice value of +19 maps to 139. So as you can see in this figure below. Next, we go to Windows scheduling. So Windows schedules threads using a priority-based preemptive scheduling algorithm. The Windows scheduler ensures that the highest priority thread will always run. The portion of the Windows kernel thread that handles scheduling is called the dispatcher. So a thread selected to run by the dispatcher will run until it is blocked, uses time slice, or is preempted by a higher priority thread. And so real-time threads can preempt a non-real-time thread. So this preemption gives a real-time thread preferential access to the CPU when the thread needs such access. Now, the dispatcher uses a 32-level priority scheme to determine the order of the thread execution. So the priorities are divided into two classes. So the variable class and the real-time classes. The variable class contains threads having priorities from 1 to 15, and then the real-time classes contains threads with priorities ranging from 16 to 31. There are also thread running at priority 0 that is used for memory management. So for Windows, the dispatcher uses a queue for each scheduling priority and traverse the set of queues from highest to the lowest until it finds a thread that is ready to run. So if there's no ready to run threads found, the dispatcher will execute a special thread called the idle thread. Now, Windows 32 API identifies several priority classes to which a process can belong. These are the real-time process priority class, high priority class, above normal priority class, normal priority class, below normal priority class, and idle priority class. All are variable except for real time. And so a thread within a given priority class has a relative priority. It can be time critical, highest, above normal, normal, below normal, lowest, and idle. So the priority of each thread is based on both the priority class it belongs to and its relative priority within the class. So as we call it, priority class and relative priority combines to give the numeric priority. So the base priority is normal within the class. And so when a thread time quantum runs out, the thread is interrupted. And so if the thread is in a variable priority class, its priority is lowered. But the priority is never lowered below the base priority. So as we have said earlier, the priority of each thread is based on both the priority class and the relative priority class. So this relationship is shown in the figure here. So the values of the priority class appears on the top row, and then the left column contains the values of the relative priorities. So for example, the relative priority of a thread is above normal priority class, normal. So again, if the value of the priority class is above normal priority class, it's normal. So the numeric priority of that thread is 10. So Windows priority class continues. So when a variable priority thread is released from a wait operation, the dispatcher boosts the priority. The amount of the boost depends on what the thread was waiting for. When a user is running an interactive program, the system needs to provide especially good performance. For this reason, Windows has a special scheduling rule for processes in the normal priority class. Windows distinguishes between the foreground process and the background process. So when a process moves into the foreground, Windows increases the scheduling quantum by some factor, typically by 3, so 3 times. This would increase the given foreground process 3 times longer to run before the time-sharing preempts occur. Next, we go to UMS. So Windows 7 introduced User Mode Scheduling, or UMS, which allows application to create and manage threads independently of the kernel. So for application that creates a large number of threads, scheduling threads in user mode is much more efficient than kernel mode thread scheduling, as no kernel intervention is necessary. So the scheduler comes from a programming language library that builds on top of UMS. So UMS scheduler comes from programming language libraries like C++, concurrent runtime, so CRT framework. So a concurrent programming framework for C++ that is designed for task-based parallelism on multi-core processor. Next, we have Solaris. So Solaris uses priority-based thread scheduling. So each thread belongs to one of 6 classes. So we have time sharing, interactive, real-time, system, fair share, and fixed priority. So a given thread can be in one class at a time. Each class has its own scheduling algorithm. So process, priorities, and time slicing are adjusted dynamically in a multi-level feedback priority queue system. So loadable table is configurable by the system administrator, sysadmin. So the figure shows that the dispatch table for scheduling time sharing and interactive threads. So these two scheduling classes includes 60 priority levels, but for brevity we display only a handful. So the dispatch table here contains the following fields. So the priority, so the class dependent priority for the time sharing and interactive class. So higher number indicates a higher priority. Next would be the time quantum. Time quantum for the associated priority. This illustrates the inverse relationship between priority and the time quantum. The lowest priority, priority 0, has the highest time quantum, and the highest priority has the lowest time quantum. Next would be the time quantum expired. So the new priority of a thread that has used its entire time quantum without blocking. So such threads are considered CPU intensive. So as shown in the table, these threads have their priorities lowered. And then last we have the return from sleep. So the priority of a thread that is returning from sleep, such as from waiting for I/O, as the table illustrates, when I/O is available for a waiting thread, its priority is boosted between 50 and 59, supporting the scheduling policy of providing good response time for interactive processes. So each scheduling class includes a set of priorities. However, the scheduling converts the class-specific priority into global priorities and select the thread with the highest global priority to run. So the selected thread runs on the CPU until it either blocks, uses its time slice, or is preempted by a higher priority thread. So if there are multiple threads with the same priority, the scheduler uses a round-robin queue. So the figure illustrates how the six scheduling classes relate to one another and how they map to global priorities. We could notice that the kernel maintains 10 threads for servicing interrupts. So from 160 to 169. So these threads do not belong to any scheduling classes and execute at the highest priority, so 160 to 169. As mentioned, Solaris has traditional, traditionally used the many-to-many model, but switched to one-to-one model beginning with the Solaris 9. So we now proceed to evaluation of the algorithms. So how do we select a CPU scheduling algorithm for a particular system? So as we saw in the previous sections, there are many scheduling algorithms, so each with its own parameters. As a result, selecting an algorithm can be difficult. The first problem is defining the criteria to be used in selecting an algorithm. So as we saw in the previous section, criteria are often defined in terms of CPU utilization, response time, or throughput. So to select an algorithm, we must first define the relative importance of these elements. So once a selected criteria have been defined, we want to evaluate the algorithms under consideration. We next describe the various evaluation methods we can use. So first on the list is the deterministic modeling. So deterministic modeling is one type of analytic evaluation. So analytic evaluation uses a given algorithm and then the system workload to produce a formula or number to evaluate the performance of the algorithm for that workload. So deterministic modeling, this method takes a particular predetermined workload and defines the performance of each algorithm for that workload. So given the example, assuming we have a workload shown below, so this uh, processes, so all 5 processes arrive at time 0 in the order given, so P1, P2, P3, P4, P5. So we have this. So let's consider the first come first serve, the shortest job first, and the round robin with the quantum of 10 milliseconds scheduling algorithms for this set of process. So which algorithm would give the minimum average waiting time? So for first come first serve algorithm, we get the average waiting time of 28 milliseconds, and then for the non-preemptive sh shortest job first is having 13 milliseconds, and the round robin algorithm with a time quantum of 10 milliseconds gives us 23 milliseconds of average waiting time. So from here we can see that in this case, the average waiting time obtained with a shortest job first policy is less than half that obtained with first come first serve scheduling. The round robin algorithm gives us an intermediate value. So that's it. Deterministic modeling is simple and fast, rather. It gives us exact numbers, allowing us to compare the algorithms. However, it requires exact numbers for input, and its answer apply only to those cases. And so the main use of deterministic modeling are in describing scheduling algorithms and providing examples. Let's proceed to queuing models. So on many systems, the process that are run vary from day to day, so there is no static set of processes or times to use for deterministic modeling. What can be determined, however, is the distribution of CPU and I/O bursts. These distributions can be measured and then approximated or simply estimated. The results will be a mathematical formula describing the probability of a particular CPU burst. Commonly, this distribution is exponential and is described by its mean. Similarly, we can describe the distribution of times when processes arrive in the system. So the arrival time distribution. So from these two distributions, it is possible to compute for the average throughput, utilization, waiting time, and so on for most algorithms. So the computer system is described as a network of servers. So with each server has a queue of waiting processes. So the CPU is a server with its ready queue, as is the I/O system with its device queue. So knowing the arrival rate and service rate, we can compute utilization, uh, average queue length, average waiting time, and so on. So this area of study is called the queuing network analysis. So as an example, let n be the average queuing length, let w be the average waiting time in the queue, and let the delta be the average arrival rate for the new process in the queue. So we expect that during the time w that a process waits, delta times w new processes will arrive in the queue. So if the system is in a steady state, then the number of processes leaving the queue must be equal to the number of processes arriving. Thus we have the formula n equals delta times w, which this equation is known as the Little's formula. This is particularly useful because it is valid for any scheduling algorithms and arrival distribution. So for example, if on average 7 processes arrive per second, and normally if 14 processes in queue, then the average waiting time per process would be 2 seconds. So let's proceed. Queuing models are limited, so we proceed to simulations. So to get more accurate evaluation of the scheduling algorithms, we can use Simulations. So running simulations involves programming a model of a computer system. So the simulator has a variable representing a clock. So as this variable value is increased, the simulator modifies the system state to reflect the activities of the device, the process, and the scheduler. And so as the simulation executes, statistics that indicate algorithm performance are gathered and are printed. So the data to drive the simulation can be generally in several ways. The most common method uses a random number generator that is programmed to generate processes, CPU burst times, arrivals, departures, and so on, according to probability distribution. So the distribution can be defined mathematically or empirically. So if the distribution is to be defined empirically, measurements of the actual system under study are taken. So a distribution-driven simulation may be inaccurate. However, because of relationship between successive events in the real system. The frequency distribution indicates only how many instances of each event occurs. It does not indicate anything about the order of their occurrence. So to correct this problem, we can use trace tapes. So we can create a trace tape by monitoring the real system and recording the sequence of actual events, as seen in this figure. So we then use the sequence to drive the simulation. Trace tapes provides an excellent way to compare two algorithms on exactly the same set of real inputs. So this method can produce accurate results for its input. Simulations can be expensive, often requires hours of computer time. A more detailed simulation provides more accurate results, but it also takes more computer time. So in addition, trace tapes can require a large amount of storage spaces. So finally, the design, coding, and debugging of the simulator can be a major task. Event simulations have limited accuracy, so the only way to completely accurately evaluate a scheduling algorithm is to code it up. So this approach puts the algorithm in the real system for evaluation under real operating conditions. The major difficulty with this approach is that it has high cost. So the expense is incurred not only in encoding the algorithm and modifying the operating system to support it, but also in reaction of the users to a constant changing operating system, where most users are not interested in building a better operating systems. They merely want to get their process executed and use their results. So a constant changing operating system does not help the user to get their work done. Another difficulty is that the environment in which algorithms is used will change. The environment will change not only in usual ways as new programs are written, and then the type of problems change, but also as a result of the performance of the scheduler. So the most flexible scheduling algorithms are those that can be altered by the system managers or by the users so that they can be tuned for a specific application or set of applications per site or per system. Another approach is to use APIs that can be modified. They can modify the priority of the process or thread. So the Java, POSIX, and Windows API provide such functions. Then the downfall of this approach is that performance tuning a system or application most often does not result in improved performance in most general situation. So that's it for my report. Thank you.